In section 6.1, we'll be discussing accumulation and definite integrals. So let's remember from Unit 5 that velocity is the rate of change of position with respect to time. If we know about velocity, we can actually recover information about position. So let's think about this problem. A truck travels along a highway at a constant velocity of 60 miles per hour for 1.75 hours. How far did it go? So let's remember from our first year physics class that distance is equal to velocity times time. So I can do 60 miles per hour times 1.75 hours. 60 times 1.75 is 105. And then if I pay attention to my units here, I would notice that the hours actually cancel out, and so my units are just miles. 105 miles. So that's how far this truck traveled. Let's think about what that means graphically. So over here I have 60 miles per hour as my velocity, and my time is on the x-axis, t equals 1.75 hours. If I think about multiplying those together, that would actually give me the area. So 60 times the 1.75 is my base times my height. That gives me the area of this rectangle. And so notice graphically, I could multiply the base times the height to get my change in position. Because when I talk about how far I went, I'm actually talking about my change in position. So with a velocity graph, if I find the area underneath that graph, I can find how far I've traveled. Now that doesn't just work when I have a constant velocity. This formula that we used up here, that really only works with constant velocity. But if we have a changing velocity, we can do the same thing. So here we have the truck is slowing down, approaching an exit ramp. And here's the velocity of the graph, or sorry, of the truck. And we want to know how far did the truck travel over these 10 seconds. So notice at the bottom here we have 10 seconds. And I'm starting up here, this is in miles per hour still. So I start at 60 miles per hour, I end at 30 miles per hour because the truck is slowing down. And so if I want to find this area, you can do the area of a trapezoid, but what I find usually is easier is to do a rectangle times, the area of a rectangle plus the area of a triangle. And so I want to look at my base and height for each of those. So here my height of my triangle is 30, my base is 10, and for my rectangle my height is 30 and my base is 10 as well. So when I go to find these areas, I'm going to do, let's keep in mind the units here. For the rectangle at the bottom, 30 miles per hour times 10 seconds plus for a triangle, it's half the base times the height, so 1/2 times 30 miles per hour times 10 seconds. What that gives us, we would have 300 here, 150 here, so this is 150, this is 300. Add those together, that gives us 450. But our units don't cancel out here. This hours doesn't cancel with a second. So what we have right now is miles per hour times seconds. And so in order to cancel that, we will have to do a unit conversion. And so we have to think about how many seconds are in an hour. Because I want this to cancel, I'll put 1 hour on top. Seconds, so 60 seconds in a minute and 60 minutes in an hour, that would give me 3,600 seconds. And now I can see how my units would cancel out. So my seconds would cancel, my hours would cancel. I'll just have to divide the 450 by 3,600, and that would give me 1/8 of a mile. Also, on problems like this, I know the units can be tricky, but just keep in mind, like, it wouldn't make sense for me to approach an exit ramp and go 450 miles. That doesn't make sense. 1/8 of a mile makes a lot more sense. So just keep that in mind in these problems. And number 3, it tells us that R of t models the rate of change in a helicopter's altitude, that's its height, in feet per second, where t is measured in seconds. Here's our graph of R of t. We want to know how much altitude the helicopter gained from 0 to 8. And then we'll also find the net change in the helicopter's altitude over these 16 seconds. So we can really think about this rate of change kind of like a velocity. It is in feet per second, so it kind of makes sense with that. And so let's go ahead and calculate from 0 to 8. And so again, when I am thinking about my rate of change here, and if I want to find how far I traveled, I will just find the area. So from 0 to 8, I have this triangle here. And so I have 1/2 my base times my height. My base is 8 seconds. My height is 40, and those units there were feet per second. And that would give me 160 feet. So again, that's the area here. Notice again, the seconds cancel out. And so just to reiterate, when I have a rate and I want to find my amount of change, I would find the area under the graph. And then it asks me, what is the net change in the helicopter's altitude over these 16 seconds? So let's pay attention to this graph. This goes below the x-axis now, or the t-axis. So let's think about what that means. This r of t is my altitude. And so if my it's the rate of change of my altitude. If my rate of change of my altitude is negative, that means my altitude is decreasing. So this means I'm going up over here, I'm going down over here. So when my rate of change is negative, that means my altitude is decreasing. So I can still find this area to figure out how far I went down. But what I'm going to do then is subtract that amount I went down from how far I went up. So I went up 160 feet, I went down some number of feet, so my net change, I would subtract those two. So I'm going to do my 160 feet that I started with, and then I'm going to subtract this area here. So my base is 8 again. My height is only 20, and then I have to do 1/2 times that. The units would end up being feet. I should have probably put the units on each of those. So that gives me 160 minus 80 feet, so that gives me 80 feet for my net change. So overall, I'm 80 feet higher than when I started. So this idea of finding area under curve motivates the need for a new calculus concept, which we call the definite integral. So when we want to find the area under a positive curve, y equals f of x, and above the x-axis from x equals a to x equals b, it can be written with this symbol. So the way we read this is the integral from a to b of f of x dx. Now the dx you can think of as just a placeholder. So think about the beginning integral as like a beginning parenthesis, and then the dx is like an ending parenthesis. So we always have an integral, the integral symbol and the dx there. You do want to pay close attention to your bounds, your a and your b. That tells you where to start and where to stop. So notice this goes from x equals a to x equals b. So we start at the bottom and then go to the top when we're reading that. So for example, when in number 4, we have a function f, and it asks me for the value of the integral from -5 to 7 of f of x dx. That means area under f of x from x equals -5 to x equals 7. And when I say area under f of x, I really mean between f of x and the x-axis. So the piece that I'm looking at is from -5, the graph here, all the way to 7. And so it's all of this area that I'm looking for, that chunk. And so I can find the area again using a trapezoid, but a lot of us don't remember that formula. And so I find it's easier for us to use a triangle, a rectangle, and another triangle. So for this triangle, we have 1/2. Our base from -5 to -1 is 4. And then our height is 6. Plus, now let's do the rectangle. Our base is 3. Our height is 6. And our last triangle, we're going from 2 to 7, so that has a base of 5, and our height of our triangle is 6 as well. So we will need to simplify those and add them together. So this is 12 plus 18 plus 15, which gives us 45. Now in this case, we're not worried about units or anything like that. We're just actually finding this value. So the area under the curve of f of x from -5 to 7 is 45. Now, as we saw in our altitude example, we know that not all curves are positive, and so we'll just have to take a special consideration when the curve goes below the x-axis. So here we have a graph of f of x. We can see that the areas of each of these regions is the value a, and so when we're talking about area, it's always positive. But when we talk about an integral, what we're going to do, if my graph is above the x-axis, my integral will be positive a. If my graph goes below the x-axis, then my integral will be negative a, whatever that value is. So let's take a look at problem number 5. So we have the regions A, B, C, and D in this figure. And it tells me the area of region A is 8, the area of region B is 6, the area of region C is 12, and the area of region D is 12 as well. It asks me to find the value of the integral from -4 to 8 f of x dx. So notice I'm not going to start until -4, and then I'll end at 8. So don't automatically assume you're using the whole graph here. Now let's try to zoom in and see which parts of my graph are positive and negative. So this area above the x-axis will be positive, and this area will be positive. This part below the x-axis will be negative. So when I want to find this integral, I'm going to have 6 minus 12 for the area below plus 12. And so that gives me an area, a total area of 6. So pay attention to when they give you these area values, they will be positive. You will have to decide if you're adding or subtracting.